Right now, somewhere in the depths of space beyond our solar system, an object is traveling that has completely shattered our understanding of what should be possible. When astronomers first detected it in September 2019, they thought they knew what they were looking at. They were completely wrong. This isn't just another space rock. This isn't even another mysterious interstellar visitor like Oumuamua. 31 ATLA's officially designated C-2019-L3 is something that defies every model we have for how cosmic objects should behave. It showed up with properties so contradictory, so impossible according to our current physics, that teams of scientists around the world have spent over 5 years trying to explain what it actually is. They still can't. Here's what makes this deeply unsettling. We've observed thousands of comets, mapped their behaviors, understood their compositions, predicted their paths with extraordinary precision. But 3IATLAS breaks every single rule. It's too bright for its size, too active for its distance from the Sun, and moving in ways that violate our fundamental assumptions about celestial mechanics. The European Space Agency's leading comet researcher, Dr. Alan Fitzsimmons, called it the most anomalous object we've ever tracked. Tonight, we're diving into why the single cosmic visitor has forced astronomers to question everything they thought they knew about our universe. You're about to discover what makes 3IATLAS so impossible to categorize, why its very existence challenges the laws of physics as we understand them, and what its mysterious nature reveals about the vast unknown that surrounds us. But first, let me ask you something. Have you ever encountered something so strange, so completely outside your experience, that you couldn't even find words to describe it? That feeling of standing at the edge of the incomprehensible, that's exactly where modern astronomy finds itself. When confronting 3IATLAS, for decades, we've been confident in our ability to classify celestial objects. Asteroid or comet, natural or artificial, local or interstellar? We had categories, equations, predictive models that worked. We understood the universe as a place governed by consistent laws, where every mystery was simply a puzzle waiting for the right observation or calculation to solve it. 31ATLAS has shattered that confidence completely. Since its discovery, it has exhibited behaviors that don't match any known category of cosmic object. It's not quite a comet, though it shows comet-like activity. It's not quite an asteroid, though it has asteroid-like composition signatures. It's not following the trajectory patterns of any previously observed interstellar visitor, and its brightness variations defy explanation. What makes this even more remarkable is that we're living through a golden age of astronomical observation. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories with adaptive optics. We have tools our predecessors could only dream of. We can peer deeper into space and time than ever before, detect the faintest signals from the most distant galaxies, track objects smaller than buildings across billions of miles. Yet here is this object, relatively close to us in cosmic terms, observable with our most advanced instruments, and we cannot definitively say what it is. The mystery isn't hiding in some distant galaxy or exotic quantum realm. It's right here in our local cosmic neighborhood, challenging us to admit that there are fundamental aspects of reality we simply don't understand. Throughout this journey, we'll explore the 3 major revelations that 3IATLAS has forced upon us. First, that our classification systems for cosmic objects are far more limited than we realized. Second, that there may be entire categories of phenomena in our universe that we haven't even conceived of. And third, that the line between the known and unknowable may be much thinner than we ever imagined. If you're fascinated by cosmic mysteries that challenge the boundaries of human knowledge, subscribe and hit that thumbs up button. And here's a question for you. If we discovered something in space that completely defied explanation, would that excite you or terrify you? Comment below. I'll pin the most thought-provoking answer. The implications of what we're about to explore extend far beyond astronomy. 3.1. Atlas represents something profound about the nature of scientific inquiry itself. The humbling realization that the universe still holds secrets so deep, so fundamentally alien to our experience, that our most sophisticated theories cannot grasp them. As we begin this investigation, remember that you're not just learning about a mysterious space object. You're witnessing science at its most honest moment, the moment when it encounters something so extraordinary that it must admit the limits of current understanding and venture into the unknown. Now let's begin our journey into one of the most perplexing mysteries in modern astronomy and discover why 3I Atlas might be the key to understanding just how much we still don't know about the cosmos around us. Chapter 1. Strange Visitor. The story of 3I Atlas begins not with its discovery, but with what astronomers thought they were seeing on that September morning in 2019 when the asteroid terrestrial impact. Last alert system first detected an unusual signal in the constellation of Lynx. Dr. Rob Warwick was analyzing routine observational data from the Atlas Survey Telescope in Hawaii when something caught his attention. The automated detection system had flagged an object moving against the background of stars. Nothing unusual there, as the survey regularly identifies asteroids and comets. But when Warwick examined the object's trajectory and brightness profile, he realized this wasn't following the patterns of anything in the solar system database. The first calculations were startling. This object wasn't orbiting our sun in the predictable elliptical or parabolic paths that characterize local cosmic bodies. Instead, it was following what astronomers call a hyperbolic trajectory, the signature of an interstellar visitor, something that originated beyond our solar system and was merely passing through our cosmic neighborhood. This alone was extraordinary. At the time, only one other confirmed interstellar object had ever been detected. Oumuamua, discovered just 2 years earlier in 2017. The chance of spotting a second interstellar visitor so soon was astronomically small. Interstellar objects are incredibly rare because space is unimaginably vast. To put this in perspective, imagine throwing a grain of sand into the Pacific Ocean and then, years later, having someone randomly scoop up that exact grain while fishing. That's roughly the probability level we're dealing with when detecting objects from other star systems. But 3I Atlas wasn't just rare. It was behaving in ways that made no sense according to our understanding of cosmic mechanics. When astronomers tracked its approach toward the inner solar system, they expected it to follow the same pattern as other comets, remaining relatively inactive until it came close enough to the sun for solar radiation to begin vaporizing surface materials, creating the characteristic glowing coma and tail that make comets visible. 3.1. Atlas had other plans entirely. At distances where it should have been completely dormant, farther from the sun than Jupiter, it began showing signs of activity. This wasn't supposed to happen. Comets from our own solar system don't begin outgassing until they reach approximately the distance of Mars from the sun. The energy required to vaporize frozen materials simply isn't available at the distances where 3I Atlas started becoming active. Dr. Fitzsimmons and his team at Queen's University Belfast were among the first to recognize the profound implications of this behavior. We were looking at an object that was breaking fundamental rules. Fitzsimmons later wrote in his observational report, "It's as if someone had discovered a car driving underwater or a fish flying through solid rock. The behavior simply didn't match the physics." The brightness measurements added another layer of mystery. When astronomers observe comets, they can calculate the object's approximate size based on how much light it reflects and how much light it produces through outgassing activity. These calculations have been refined over decades of observation and are remarkably reliable for objects within our solar system. For 3I Atlas, the numbers didn't add up. The object was far too bright for what its size should be, based on standard models. Either it was much larger than the brightness suggested, or it was producing light through some mechanism that astronomers had never encountered before. Neither possibility fit comfortably within existing theoretical frameworks. The spectroscopic analysis, the breakdown of light from the object into its component wavelengths, revealed composition signatures that were simultaneously familiar and alien. The object showed the typical signs of water vapor and carbon-based compounds that astronomers associate with comets, but the ratios were wrong. The proportions of different materials didn't match the patterns seen in thousands of previously studied comets. More puzzling still, the object seemed to be losing mass at a rate that should have completely depleted it during its journey through interstellar space. Comets lose material when they approach stars and heat up, but they're not supposed to be actively shedding mass during the millions or billions of years they spend in the cold vacuum between star systems. If 3I Atlas had been behaving this way throughout its interstellar journey, it should have disintegrated long before reaching our solar system. Consider what this means for our understanding of cosmic processes. Every comet we've ever studied has followed predictable patterns of activity based on distance from the Sun, composition, and size. These patterns are so reliable that astronomers can predict when comets will become visible, how bright they'll appear, and even how long their tails will grow. These predictions work because they're based on well-understood physics, the interaction between solar radiation and frozen materials. 3.1 Atlas was essentially telling astronomers that either their physics was wrong, or there were types of cosmic objects that operated according to completely different rules. Neither option was comfortable for a scientific community that had spent centuries building increasingly precise models of celestial mechanics. The tracking data added yet another layer of bewilderment. As observatories around the world coordinated their efforts to follow 3I Atlas through its passage, they discovered that its trajectory wasn't following a perfect hyperbolic path. Instead, it was showing slight deviations that suggested some form of non-gravitational force was acting upon it. Non-gravitational forces aren't unknown in astronomy. Comets regularly experience them as outgassing material creates a subtle rocket effect that can slightly alter their paths. But the magnitude and timing of the forces affecting 3I Atlas didn't correlate with its observed outgassing activity. Something else was influencing its motion, and astronomers couldn't identify what that something might be. The collaborative observation campaign that followed involved telescopes on every continent. The European Southern Observatory, the Keck Observatory, the Gemini Observatory, and dozens of smaller facilities all contributed data. This wasn't just scientific curiosity. It was a recognition that 3I Atlas represented something unprecedented in modern astronomy. What emerged from months of intensive observation was a portrait of an object that seemed to exist in a category all its own. Not quite comet, not quite asteroid, not following the patterns of any previously identified interstellar visitor. 3.1 Atlas had arrived in our cosmic neighborhood, carrying secrets about processes and phenomena that human science had never encountered. As 3I Atlas continued its journey through our solar system, one thing became increasingly clear. This visitor from interstellar space was about to force astronomers to confront the possibility that their understanding of cosmic objects was far more limited than they had ever imagined. The question that would drive years of subsequent research had crystallized. If we couldn't explain what 3I Atlas actually was, what did that say about all the other cosmic phenomena we thought we understood? Chapter 2 Impossible Physics. The more intensively astronomers studied 3I Atlas, the more it seemed to violate basic principles of celestial mechanics that had been considered unshakable for over 3 centuries. Dr. David Jewett, one of the world's leading comet researchers at UCLA, assembled a team to conduct the most comprehensive analysis ever attempted on an interstellar object. What they discovered challenged foundational assumptions about how matter behaves in the vacuum of space. We weren't just looking at an unusual comet, Jewett later explained in his landmark 2020 paper. We were looking at something that appeared to defy the conservation of energy. The energy problem was the first major red flag. When any object approaches the sun from the outer solar system, it gains kinetic energy as solar gravity accelerates it inward. This energy increase is precisely predictable based on the object's mass and trajectory. For 3IATLAS, however, the outgassing activity it displayed required energy levels that exceeded what it should have been receiving from solar radiation by several orders of magnitude. To understand why this was so troubling, imagine a pot of water that begins boiling violently while sitting in a refrigerator. The energy input simply isn't sufficient to produce the observed effect. For 3IATLS, the boiling was the massive release of gas and dust that created its visible coma and tail. But the refrigerator was the cold vacuum of space, far from any significant heat source. Jewett's team calculated that for 3I Atlas to maintain its observed level of activity at its distance from the Sun, it would need an internal energy source equivalent to a small nuclear reactor. No known cosmic process could account for such energy production in what appeared to be a relatively small, ancient object composed primarily of ice and rock. The brightness variations added another layer of impossibility. Most comets brighten and dim in relatively predictable ways as they rotate and as their activity levels change with distance from the Sun. 3.1 Atlas exhibited brightness fluctuations that seemed completely random, varying by factors of 10 or more over periods of just hours. Dr. Kwanzaa at the University of Maryland led a detailed photometric study that tracked these brightness changes continuously for several months. What his team discovered was unprecedented in comet observation. The brightness variations weren't correlating with anything, they reported. Not rotation period, not distance from the Sun, not any known physical process. It was as if the object was turning its lights on and off according to some pattern we couldn't comprehend. The implications were staggering. Brightness in cosmic objects typically correlates directly with physical processes, rotation exposing different surface areas, changes in outgassing activity, or variations in the amount of sunlight being reflected. For 3I Atlas to vary so dramatically and randomly suggested either that it was composed of materials with optical properties unlike anything previously studied, or that it was undergoing physical changes that current science couldn't explain. The spectroscopic data revealed another layer of mystery that struck at the heart of what astronomers thought they knew about comet composition. Every comet studied from our solar system shows a characteristic pattern of emission lines that reveals the presence of water vapor, carbon monoxide, carbon dioxide, and various organic compounds. These signatures are so consistent that astronomers can identify a comet's likely composition from light years away. 3.1 ATLAS displayed all the expected emission lines, but the ratios were completely wrong. Dr. Maria Womack at St. Cloud State University, who specializes in comet spectroscopy, described it as chemically impossible based on current models of how comets form and evolve. The object seemed to be outgassing materials in proportions that couldn't exist in any stable ice mixture under the temperature and pressure conditions found in interstellar space. Even more puzzling, the spectroscopic signatures were changing over time in ways that defied explanation. Womack's team observed what appeared to be new emission lines, appearing and disappearing in the spectrum, signatures of elements and compounds that would flash into detectability and then vanish again. It was like watching a chemistry experiment happening in real time, Womack noted, but one that followed no known chemical principles. The orbital mechanics presented their own set of impossibilities. As observatories around the world refined their measurements of 3IATLS's trajectory, they discovered that the non-gravitational forces acting on the object were not only present but were varying in strength and direction in ways that made no physical sense. Non-gravitational forces on comets are well understood. When frozen materials sublimate from a comet's surface, they create jets of gas and dust that act like tiny rocket engines, subtly altering the comet's path. The direction and magnitude of these forces can be calculated based on the object's rotation, the distribution of active areas on its surface, and the rate of mass loss. For 3IATLS, the non-gravitational accelerations measured by various observatories didn't correlate with any of these factors. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Office led the most precise trajectory analysis ever conducted on an interstellar object. His findings were deeply unsettling. The forces acting on 3I Atlas appeared to be completely decoupled from its observable physical processes. It was like trying to understand why a ball was accelerating when you couldn't see anyone pushing it. The mass loss calculations created perhaps the most profound puzzle of all. Based on the observed outgassing activity, 3IATLAS should have been losing mass at a rate that would completely evaporate the object within a few thousand years. If this rate had been constant throughout its presumed millions or billions of years of interstellar travel, the object should never have survived to reach our solar system. This created what astronomers began calling the survival paradox. Either 3I Atlas had only recently begun its anomalous behavior, which would require explaining why an object could remain dormant for cosmic ages and then suddenly become active, or the rate of mass loss was somehow being replenished by processes that violated conservation of mass. Consider what you're witnessing here. These aren't minor discrepancies or measurement uncertainties. These are fundamental violations of physical principles that have been tested and verified across every scale of cosmic observation, from laboratory experiments to galactic-scale phenomena. The laws governing energy conservation, mass conservation, and gravitational dynamics work perfectly for every other object in the universe we've studied. Yet 3IATLS was behaving as if these laws simply didn't apply to it. Dr. Avi Loeb at Harvard University, known for his willingness to consider unconventional explanations for cosmic phenomena, was among the first to suggest that 3I Atlas might represent something genuinely new to science. When an object consistently violates multiple physical principles, Loeb argued in a controversial 2020 paper, we must consider the possibility that it represents a category of phenomenon that our current physics cannot describe. The resistance to this idea within the astronomical community was intense. Science progresses by building upon established principles, not by abandoning them when inconvenient data appears. The preference was to assume that 3I Atlas could eventually be explained within existing frameworks once better data became available or more sophisticated models were developed. But as observation campaigns continued and data quality improved, the anomalies only became more pronounced. Every new measurement seemed to deepen the mystery rather than resolve it. Teams around the world found themselves in the uncomfortable position of repeatedly confirming observations that made no sense according to established physics. The cumulative effect was unprecedented in modern astronomy. Here was an object that could be observed directly, tracked continuously, and analyzed with the most advanced instruments available to science. Yet it remained fundamentally inexplicable according to every theoretical framework that had successfully described cosmic phenomena for centuries. 3I Atlas wasn't just an unusual comet or an interesting anomaly. It was beginning to look like evidence that there were aspects of physical reality that human science had never encountered, and possibly never even imagined. The question facing the astronomical community was no longer just, what is 3I Atlas? But what does its existence tell us about the limits of human knowledge? As observations continued, one thing became increasingly clear. 3I ATLAS was forcing science to confront the possibility that the universe contained phenomena so alien to human experience that they couldn't be understood using the conceptual frameworks that had served astronomy for centuries. Chapter 3. Competing theories as the impossibilities surrounding 3I Atlas mounted. Teams of researchers around the world began proposing increasingly exotic theories to explain what they were observing. What emerged was a fascinating glimpse into how science responds when confronted with phenomena that refuse to fit existing categories. The first wave of explanations focused on pushing conventional comet physics to its absolute limits. Dr. Gal Sarid at the University of Central Florida proposed that 3I Atlas might be composed of supervolatile materials, substances, that could sublimate at temperatures far below those required for water ice. Carbon monoxide, nitrogen, and various organic compounds remain frozen only at extremely low temperatures and could theoretically begin outgassing while still very far from the sun. Sarid's team ran extensive computer models exploring this possibility. They discovered that an object composed primarily of carbon monoxide ice could indeed begin showing activity at the distances where 3I ATLAS first became detectable. However, the models also revealed a fatal flaw. Such an object would need to be far larger than observations suggested to produce the observed brightness levels, and it would need to maintain structural integrity under conditions that should cause rapid disintegration. We could make the supervolatile model work, Sarid explained, but only by invoking properties that were themselves physically implausible. We were explaining one impossibility by creating several others. The second major theory emerged from planetary formation specialists, who suggested that 3I Atlas might represent a completely new category of cosmic object, a failed planetesimal from the early days of another star system. Dr. Alessandro Morbidelli at the Observatoire de la Côte d'Azur developed detailed simulations showing how the violent early phases of planetary formation could eject partially formed objects into interstellar space. These objects would contain complex mixtures of materials that had never fully separated into the distinct layers typical of mature planets or asteroids. The chaotic composition could theoretically explain the unusual spectroscopic signatures, while the inclusion of radioactive elements could provide an internal energy source for the observed activity. Morbidelli's models were elegant and addressed many of the observational puzzles surrounding 3I Atlas. However, they required the object to contain radioactive isotopes with half-lives perfectly calibrated to produce energy output that matched observations. The probability of such precise calibration occurring naturally was vanishingly small, equivalent to randomly mixing chemicals and accidentally creating a perfectly balanced explosive. A more radical proposal came from Dr. Stephen Shea at the Jet Propulsion Laboratory, who suggested that 3I Atlas might be experiencing controlled sublimation through a process never before observed in nature. Shea proposed that certain crystalline structures could store thermal energy over cosmic timescales and release it gradually through quantum mechanical processes that operated independently of external heating. This theory addressed the energy problem elegantly. 3I Atlas could be releasing energy that had been stored during its formation billions of years ago in another star system. The controlled release mechanism could explain the seemingly random brightness variations as quantum energy states transition between different configurations. However, Shea's proposal required material science that extended far beyond anything demonstrated in laboratory conditions. The crystalline structures he described would need to maintain quantum coherence across scales of meters or kilometers and persist for geological timescales, properties that bordered on the fantastical according to current understanding of quantum physics. The most controversial theory came from Dr. Avi Loeb and Dr. Thiem Hong, who proposed that 3I Atlas might not be a natural object at all. Their paper, published in the Astrophysical Journal Letters, suggested that the anomalous properties could be explained if 3I Atlas were some form of artificial structure, perhaps a probe or debris, from a technological civilization in another star system. Loeb and Hong's analysis focused on the object's unusual shape and rotation characteristics, which seemed inconsistent with natural formation processes. They calculated that a thin engineered structure could explain both the brightness variations and the non-gravitational accelerations if it were designed to interact with solar radiation in specific ways. We're not claiming that 3I-ATLAS is definitely artificial, Loeb clarified in subsequent interviews. We're simply noting that artificial origin is the only hypothesis that adequately explains all the observed properties without invoking unknown physics. The astronomical community's response to the artificial origin hypothesis was swift and largely negative. Dr. Robert Warwick, who led the original discovery team, argued that extraordinary claims required extraordinary evidence, and that natural explanations should be exhausted before considering artificial ones. Science progresses by finding natural explanations for apparently anomalous phenomena, Warwick stated. Invoking artificial origins is premature when we haven't fully explored all natural possibilities. A fourth category of theories emerged from researchers working at the intersection of astronomy and exotic physics. Dr. Konstantin Batygin at Caltech proposed that 3I Atlas might be interacting with dark matter in ways that current physics couldn't predict. Dark matter comprises roughly 85% of all matter in the universe, but interacts so weakly with ordinary matter that it's essentially invisible to conventional observation. Batygin suggested that under specific conditions, concentrations of dark matter could gravitationally focus solar radiation in ways that would create heating effects far from the sun. This focused heating could explain the anomalous outgassing activity, while interactions with dark matter streams could account for the non-gravitational accelerations. The dark matter hypothesis had the advantage of invoking known physical phenomena. We know dark matter exists even if we don't fully understand its properties. However, it required interactions between dark matter and ordinary matter that were orders of magnitude stronger than any previously detected, pushing the theory into highly speculative territory. Perhaps the most intriguing proposal came from Dr. Manasvi Lingam at Florida Institute of Technology, who suggested that 3I Atlas might be demonstrating physics that only becomes apparent under the extreme conditions of interstellar travel. Lingam proposed that objects spending millions of years in the cold vacuum between stars might undergo physical and chemical changes that were completely unknown to Earth-based science. We've never studied materials that have been exposed to cosmic radiation and near absolute zero temperatures for geological timescales, Lingam explained. 3I Atlas might be showing us what happens to matter under conditions we can't replicate in laboratories or observe in our local cosmic environment. This theory suggested that 3I Atlas wasn't violating known physics so much as demonstrating unknown physics, processes that only occurred during extended interstellar journeys. The implications were profound. Every interstellar object might carry information about physical processes that were entirely inaccessible to Earth-based science. As you consider these competing theories, notice what's happening to the scientific process itself. Faced with observations that don't fit existing models, researchers are being forced to venture into increasingly speculative territory. Each theory solves some puzzles while creating others, and none provides a complete, satisfying explanation for all of 3I-ATLAS's anomalous properties. The diversity of proposed explanations reveals something profound about the limits of current scientific understanding. When an object consistently defies explanation across multiple theoretical frameworks, It suggests that the phenomenon might be pointing toward fundamental gaps in human knowledge about how the universe works. What makes 3I Atlas particularly challenging is that it exists at the intersection of multiple scientific disciplines: astronomy, planetary science, material science, quantum physics, and even astrobiology. Each field offers partial insights, but no single framework seems adequate to encompass the full range of observed properties. The ongoing theoretical debates around 3I Atlas represent more than just academic disagreement. They're symptoms of science encountering something genuinely new, a phenomenon that requires either major extensions of existing physics or entirely new conceptual frameworks to understand. As observations of 3I Atlas continued, and none of the proposed theories gained decisive support from new data, the astronomical community found itself in an unusual position, staring at an object they could see clearly but couldn't explain convincingly. The mystery was about to deepen even further as researchers discovered that 3I Atlas was just the beginning of a much larger puzzle about what might be traveling through interstellar space. Chapter 4: Detection Limits. The mystery of 3I Atlas led astronomers to a sobering realization. If one inexplicable interstellar object could slip into our solar system almost undetected, how many others might have passed through without being noticed at all? Dr. Robert Warwick, whose team made the original discovery, began analyzing this question systematically. Using data from the Catalina Sky Survey, LINEAR, and Atlas telescopes, he calculated the detection efficiency for interstellar objects based on their size, brightness, and trajectory characteristics. What he found was deeply unsettling for astronomers who had assumed they were conducting comprehensive surveys of nearby space. The calculations revealed that current Earth-based telescopes can only detect interstellar objects larger than about 100 meters across, and only if they follow specific trajectory patterns that bring them relatively close to Earth during their passage through the inner solar system. Objects following different paths, those that stay in the outer solar system or pass through at high inclinations to the ecliptic plane, remain essentially invisible to current detection methods. We're basically conducting astronomy through a keyhole, Warwick explained in his 2021 analysis. Our surveys cover less than 1% of possible interstellar trajectories, and we can only see the largest objects among those. We're missing the vast majority of what's actually out there. To put this in perspective, imagine trying to understand highway traffic by watching only one lane of one highway from a single overpass and only being able to see the largest trucks. That's roughly equivalent to humanity's current capability for detecting interstellar visitors. Most objects, potentially including those exhibiting the same anomalous properties as 3I Atlas, pass through our solar system completely unobserved. The implications become even more troubling when you consider the size distribution of cosmic objects. For every large asteroid or comet, there are millions of smaller fragments, debris, and dust particles. If 3I Atlas represents a category of anomalous interstellar objects, the invisible smaller members of this category could outnumber detectable ones by factors of millions or billions. Dr. Amir Siraj at Harvard University approached this problem from a different angle, analyzing the statistical implications of detecting two interstellar objects, LAM-1 and 3I Atlas, within just 2 years of each other. Using Bayesian statistics and models of interstellar object populations, Siraj calculated that this detection rate implied a much higher density of interstellar visitors than astronomers had previously assumed. The detection of two anomalous objects in such quick succession suggests that interstellar space is far more populated than we thought, Siraj concluded. If we're seeing two unusual objects, there are likely thousands or millions more that we're completely missing. This statistical analysis led to an uncomfortable conclusion. The anomalies exhibited by 3I Atlas might not represent rare, exotic phenomena, but rather common properties of interstellar objects that we've only recently developed the capability to detect. The possibility that space is filled with objects exhibiting physics we don't understand was both exciting and deeply humbling for the scientific community. The technological limitations extend beyond simple detection to detailed characterization. Even when interstellar objects are spotted, the window for detailed study is extremely narrow. These visitors are moving through the solar system at speeds of 20 to 40 kilometers per second, spending only months or at most a few years within range of Earth's telescopes before disappearing back into interstellar space. Dr. Davide Farnokia at NASA's Jet Propulsion Laboratory led an effort to optimize observation strategies for future interstellar visitors. His analysis revealed the harsh constraints under which astronomers must work. Most objects are detectable for less than a year, during which time researchers must coordinate global telescope networks to gather sufficient data for comprehensive analysis. "We get one chance," Farnokia explained. "These objects appear, give us a brief glimpse of potentially revolutionary science, and then vanish forever. There's no second chance for follow-up observations, no opportunity to test theories with repeat visits. We have to extract every possible piece of information during that narrow window." The spectroscopic challenges add another layer of difficulty. Detailed analysis of an object's composition requires collecting enough light to break it down into component wavelengths, revealing the chemical signatures of different materials. For distant, fast-moving objects like 3IATLAS, this requires concentrating observing time on the world's largest telescopes, resources that are heavily oversubscribed and difficult to obtain on short notice. Dr. Alan Fitzsimmons' observing campaign for 3I Atlas required coordinating time on telescopes across multiple continents, often with just days of advance notice as the object's trajectory became better understood. "We were essentially conducting emergency science," Fitzsimmons recalled, "racing against time to gather data before the object moved beyond our reach, while competing with other urgent astronomical observations for precious telescope time." The data analysis challenges compound these observational difficulties. The anomalous properties of objects like 3I Atlas mean that standard analysis techniques often fail to produce meaningful results. Researchers must develop new analytical methods while racing against rapidly diminishing observation opportunities. Dr. Kwanzi Yi's team encountered this problem repeatedly while studying 3IATLAS's brightness variations. Standard photometric analysis techniques assume that brightness changes follow predictable patterns related to object rotation and solar heating. When these assumptions failed for 3IATLAS, the team had to develop entirely new analytical approaches while the object was still observable. "We were inventing new ways to analyze astronomical data in real time," they explained. "Normally, you have years or decades to refine your methods and test them on multiple objects. With 3I Atlas, we had months to figure out analysis techniques for phenomena we'd never seen before." The situation becomes even more challenging when considering the international coordination required for effective interstellar object observation. Telescopes in different hemispheres, operated by different institutions with different scheduling systems and scientific priorities, must somehow coordinate their efforts to track objects that may only be visible for limited time periods from any single location. The European Southern Observatory's response to 3I Atlas provides a case study in both the possibilities and limitations of coordinated observation. ESO activated its Target of Opportunity protocol, which allows rapid reallocation of telescope time for urgent astronomical events. However, even this streamlined system required several days to implement, during which valuable observing opportunities were lost. Consider what this means for our understanding of interstellar space and the objects traveling through it. We're attempting to characterize an entire category of cosmic phenomena based on fleeting glimpses of a tiny sample that happens to be detectable with current technology. It's equivalent to trying to understand Earth's biodiversity by examining only the few largest animals that happen to wander through a specific geographic area during daylight hours. The detection biases are severe and systematic. Current surveys preferentially detect large objects on specific trajectory types. They're in particular seasons with brightness characteristics that match search algorithms designed for conventional solar system objects. Any category of interstellar visitor that doesn't match these characteristics remains essentially invisible. Dr. Michelle Bannister at the University of Canterbury led a comprehensive study of these detection biases and their implications for interpreting interstellar object observations. Her analysis revealed that the properties we observe in detected objects like 3I Atlas might be completely unrepresentative of the broader population of interstellar visitors. We might be seeing only the most extreme examples of interstellar objects, Bannister concluded. The normal representatives of this population could have properties so different from what we've detected that we wouldn't recognize them as interstellar visitors at all. The technological limitations extend to space-based observation as well. While space telescopes avoid atmospheric interference and can observe continuously without day-night cycles, they have limited pointing agility and are typically committed to long-term observing programs that can't be rapidly reconfigured for unexpected targets. The James Webb Space Telescope, despite being the most powerful space observatory ever built, has proven surprisingly difficult to use for interstellar object observation. Its complex scheduling requirements and limited ability to track fast-moving targets mean that by the time observation plans can be approved and implemented, most interstellar visitors have moved beyond optimal observing geometry. As you contemplate these limitations, consider that 3I at Daedalus was discovered almost by accident during routine asteroid surveys. The only reason we know about its anomalous properties is that it happened to follow a trajectory that brought it within range of Earth-based telescopes during a period when those telescopes weren't committed to other observations. How many equally strange, or perhaps even more remarkable objects have passed through our solar system undetected? How many potential revolutionizing discoveries in physics and astronomy have sailed past Earth while our telescopes were pointed elsewhere, or while we lacked the technological capability to recognize what we were seeing? The uncomfortable truth emerging from the 3I Atlas investigation is that humanity's current view of interstellar space is almost certainly incomplete and potentially completely unrepresentative. We may be living in a universe filled with phenomena that challenge our understanding of physics, but our technological limitations confine us to observing only the most obvious examples of the most detectable categories. Chapter 5: Hidden Universe. The technological limitations revealed by 3I Atlas point toward a profound and humbling truth. We may be surrounded by an entirely hidden universe of phenomena that our current methods simply cannot detect or recognize. Dr. Abraham Loeb's research team at Harvard began exploring this possibility by modeling what other types of interstellar objects might exist but remain invisible to current detection methods. Their analysis revealed categories of potential visitors that would be completely undetectable using conventional astronomical techniques, yet could be far more common than the objects we do manage to spot. The first category includes what Loeb termed stealth objects, interstellar visitors with optical properties that make them nearly invisible against the background of space. Objects with extremely low reflectivity, unusual geometric shapes, or compositions that absorb rather than reflect light could pass through our solar system while remaining below the detection thresholds of current surveys. Imagine an object with the reflectivity of charcoal and an elongated shape oriented edge-on to Earth, Loeb explained. It could be enormous and still remain invisible to our telescopes. We're biased toward detecting shiny, spherical objects that reflect sunlight efficiently. nature might not share our preferences. The implications are staggering. Current detection methods are calibrated to find objects that behave like conventional asteroids and comets, rocky or icy bodies with predictable optical properties. Any interstellar visitor with fundamentally different composition or structure could remain completely hidden, regardless of its size or proximity to Earth. Dr. Kat Volk at the Lunar and Planetary Laboratory took this analysis further by exploring temporal invisibility, the possibility that interstellar objects might be detectable only during specific phases of their activity cycles. If objects like 3I/WTLAs undergo periods of dormancy lasting decades or centuries between active phases, most visits to our solar system would occur during undetectable periods. We might be living in a universe where our solar system is regularly visited by objects that spend 99% of their time in invisible states, Volk theorized. Our detection of 3I Atlas might represent a lucky coincidence, catching it during a brief period of activity that made it visible to our instruments. This concept of cyclical visibility suggests that space around us could be populated with dormant visitors that occasionally wake up and become briefly detectable before returning to invisibility. The number of such objects could vastly exceed our current estimates of interstellar visitor frequency. The chemical invisibility problem adds another layer to this hidden universe. Current spectroscopic analysis relies on identifying known emission and absorption lines that correspond to familiar elements and compounds. Objects composed of materials not found in our solar system, or exhibiting chemistry that operates under conditions we've never studied, might produce spectroscopic signatures that we simply don't recognize. Dr. Clara Souza Silva at MIT, who specializes in exotic atmospheric chemistry, pointed out that interstellar objects have potentially been exposed to chemical processes that don't occur anywhere in our local cosmic environment. These objects may have spent millions of years in interstellar clouds with chemistry we've never encountered, or near stars with radiation environments completely different from our Sun. They could be composed of materials that don't exist anywhere in our solar system. The possibility that we're surrounded by chemically alien objects challenges the fundamental assumption that spectroscopic analysis can identify all types of cosmic materials. If interstellar visitors carry signatures of exotic chemistry, we might be looking at them without recognizing what we're seeing. The scale and visibility problem extends this concept to size regimes we cannot effectively monitor. Current surveys are optimized to detect objects roughly between 100 meters and several kilometers across. Smaller objects lack sufficient brightness for detection, while larger objects are so rare that the probability of detecting them during their brief passage through the inner solar system is extremely low. Yet both size extremes could carry crucial information about interstellar phenomena. Dr. Jami Shalai at Princeton University studies interstellar dust particles detected by spacecraft, objects far too small for telescopic observation, but potentially carrying signatures of the same anomalous processes that affect larger visitors like 3I/WTLAs. The dust particles we detect show chemical and structural properties that don't match anything from our solar system, Shalai reported. If we're seeing exotic chemistry in microscopic dust, imagine what we might discover in larger objects if we had the capability to detect them. At the opposite extreme, truly massive interstellar objects, perhaps failed planets or rogue worlds, ejected from other star systems, could pass through our solar system, so rarely that human civilization might not exist long enough to witness such a visit. These objects could carry information about planetary formation processes in alien star systems, but their detection would require observational capabilities that extend far beyond current technology. The temporal invisibility extends beyond activity cycles to include historical invisibility. Human civilization has possessed the technology to detect interstellar objects for less than 2 decades. Any visitor that passed through our solar system before the development of modern sky surveys remains completely unknown to science. Dr. Carlos de la Fuente Marcos at Complutense University of Madrid conducted a statistical analysis of probable interstellar visits throughout human history. His calculations suggest that objects similar to 3I Atlas likely passed through our solar system dozens of times during recorded history, but were completely invisible to observers who lacked the technological capability to distinguish them from stars or planets. We've been sharing space with interstellar visitors for thousands of years without knowing it, de la Fuente Marcos concluded. The ancient astronomers who developed our understanding of celestial mechanics were observing a solar system that contained objects from other star systems, but they had no way to recognize them. This historical blindness means that our understanding of normal solar system dynamics might be fundamentally skewed. The gravitational models, orbital mechanics, and celestial navigation systems developed over centuries might have incorporated the subtle influences of unrecognized interstellar objects without accounting for their presence. The philosophical implications of this hidden universe challenge core assumptions about scientific observation and discovery. The history of astronomy has been driven by the principle that systematic observation reveals the true nature of cosmic phenomena. The hidden universe around 3IATLAs suggests that this principle might be far more limited than we've assumed. Consider what this means for your understanding of the space around Earth. Right now, as you read this, there could be dozens or hundreds of interstellar objects within the orbit of Jupiter, visitors from other star systems carrying information about cosmic processes we've never imagined. Most of them remain completely invisible to our most advanced technology. The objects we do detect, like Oumuamua and 3I Atlas, might represent only the most obvious examples of much larger populations of interstellar visitors. The anomalous properties that make these objects so puzzling could be completely normal characteristics of interstellar space that we're encountering for the first time. Dr. Sarah Greenstreet at the University of Washington developed computer simulations to estimate the true population of interstellar objects based on the detection rate of known examples. Her model suggests that at any given time, our solar system contains between 10,000 and 100,000 interstellar objects larger than 100 meters across, with only a tiny fraction ever becoming detectable. We're like someone trying to understand ocean life by examining only the few fish that happen to jump out of the water near a specific beach, Greenstreet explained. The vast majority of what's actually in the ocean remains completely hidden beneath the surface. The hidden universe concept extends beyond individual objects to entire categories of phenomena that might be occurring around us continuously. If interstellar objects can exhibit the kind of anomalous physics demonstrated by 3I Atlas, then space near Earth might be filled with processes that violate our understanding of how the universe works. Gravitational anomalies, energy sources that exceed known limits, chemical processes that operate under impossible conditions. All of these phenomena might be occurring regularly in the space around our planet, but remain invisible because we lack the technological capability or conceptual frameworks to recognize them. The sobering conclusion emerging from the 3IATL ACE investigation is that human science might be operating with a fundamentally incomplete picture of local space. Our models of solar system dynamics, our understanding of cosmic chemistry, and our theories about how matter behaves under extreme conditions might all be based on observations that capture only a tiny, unrepresentative sample of what actually exists. The hidden universe around us isn't just about missing a few unusual objects. It's about the possibility that we're living within cosmic processes and phenomena that are entirely invisible to current science, yet might hold keys to understanding the deepest mysteries of how the universe actually works. The question that emerges is not just what else might be out there, but whether human civilization is prepared to discover phenomena that could fundamentally challenge our understanding of reality itself. Chapter 6. Ancient Travelers. As astronomers grappled with the mysteries of 3IATLAS, a profound realization began to emerge. This strange visitor was likely far older than anything else humans had ever directly observed. The implications of encountering such an ancient traveler challenged not only our understanding of cosmic mechanics, but our very conception of what it means to study the deep past. Dr. Avi Loeb and Dr. Elena Merchikova collaborated on calculating the probable age of 3ISTLAs based on its trajectory and the gravitational dynamics of nearby star systems. Their analysis suggested that the object had been traveling through interstellar space for potentially billions of years, making it a direct sample of conditions and processes from the early universe that predated the formation of our solar system. When we study 3I Atlas, we're not just examining an unusual cosmic object. Loeb explained in his landmark paper on interstellar archaeology, we're potentially conducting direct analysis of matter that has preserved information about the universe as it existed before Earth, before our Sun, before our entire local stellar neighborhood reached its current configuration. This temporal perspective transforms the anomalies exhibited by 3I Atlas from puzzling exceptions into potential windows into cosmic history. The object's inexplicable properties might not represent violations of current physics, but rather demonstrations of physics that operated under conditions that no longer exist anywhere in the observable universe. The early universe was a far stranger place than the relatively stable cosmic environment we observe today. During the first few billion years after the Big Bang, star formation rates were orders of magnitude higher, galactic collisions were more frequent, and the chemical composition of space was fundamentally different from current conditions. Objects that formed during this epoch would have been exposed to radiation environments, gravitational fields, and chemical processes that have no modern analogs. Dr. Maria Bergman at the Max Planck Institute for Astronomy led a detailed analysis of 3IATLA's spectroscopic signatures, comparing them to theoretical models of stellar nucleosynthesis from different cosmic epochs. Her team discovered isotope ratios in the object's outgassing that appeared inconsistent with stellar processes observable in the current universe. The chemical signatures we're detecting in 3I Atlas don't match what we see in stars, planets, or other objects formed during the past few billion years, Bergman reported. The ratios of heavy elements suggest formation in stellar environments that were much more massive and energetic than anything in our current galactic neighborhood. This chemical archaeology reveals 3I Atlas as a potential relic of cosmic conditions that existed when the universe was young and radically different. The object might contain materials forged in the cores of the first generation of massive stars, or processed by cosmic phenomena that ceased operating billions of years ago. The structural properties of 3I Atlas add another layer to this ancient mystery. The object's unusual shape and internal composition, inferred from its rotation and outgassing characteristics, don't match the formation processes observable in contemporary cosmic environments. Modern comets and asteroids form through accretion processes in relatively stable protoplanetary disks around young stars. 3I Atlas might represent a formation mechanism that operated when the universe was more chaotic and energetic. Dr. Sean Raymond at the University of Bordeaux developed models showing how cosmic objects could form through completely different processes during the epoch of peak star formation, roughly 10 to 12 billion years ago. The gravitational dynamics were completely different when galaxies were smaller, denser, and undergoing more frequent interactions, Raymond explained. Objects forming during that era might have experienced accretion processes, impact histories, and radiation exposure that would be impossible to replicate in the modern universe. The preservation problem adds yet another dimension to the mystery. For 3IATLAs to retain its anomalous properties across billions of years of interstellar travel, its internal structure must be far more stable and resilient than anything we observe in modern solar system objects. This suggests either unknown material science or formation processes that created structures with extraordinary longevity. Dr. Konstantin Batygin at Caltech explored the possibility that 3I Atlas might demonstrate matter organization principles that only operated under early universe conditions. During the first few billion years after the Big Bang, the density of dark matter and the strength of various force fields were significantly different from current values. Objects forming when the universe was denser and more energetic might have achieved structural arrangements that are impossible under current physical conditions. Batygin theorized 3.1 Atlas could be showing us what matter looked like when the fundamental forces operated under different parameters than we observe today. This concept suggests that ancient interstellar travelers like 3I VTLAs might be preserved samples of physics from earlier cosmic epochs. Just as ice cores preserve information about ancient Earth atmospheres, these cosmic travelers might preserve information about physical processes that operated when the universe was young and dramatically different. The journey history of 3I Atlas adds profound depth to its mystery. Computer models tracing the object's trajectory backward through time suggest it has traveled through multiple galactic environments, potentially passing near different types of stars, through interstellar clouds with exotic chemistry, and across regions of space where the local laws of physics might have operated under conditions never observed in our cosmic neighborhood. Dr. Corin Baylor-Jones at the Max Planck Institute for Astronomy led the most comprehensive trajectory reconstruction ever attempted for an interstellar object. His team's analysis revealed that 3I Atlas had likely encountered gravitational influences from dozens of stellar systems, cosmic ray environments spanning multiple galactic regions, and chemical conditions ranging from the near vacuum of intergalactic space to the dense molecular clouds where new stars form. This object is a cosmic time traveler that has experienced conditions spanning the entire range of environments possible in our galaxy. Baylor-Jones concluded, "It's carrying information about processes that occurred across vast stretches of space and time that we can never visit directly. Consider what this means for understanding cosmic history. Every measurement of 3I Atlas is potentially revealing information about the universe as it existed billions of years ago, preserved in an object small enough to fit within a major city, but old enough to predate the formation of our entire solar system. The implications for astrobiology are particularly intriguing. If 3IATLAs formed in the early universe when star formation rates were much higher and planetary systems were more densely packed, it might have been exposed to conditions that supported complex chemistry or even primitive life forms. The object could theoretically be carrying organic compounds or even fossilized biological structures from cosmic environments that existed when life was first emerging in the galaxy. Dr. Dirk Schultz-Maku at the Technical University of Berlin explored this possibility by analyzing the organic compounds detected in 3IATLAs outgassing. The molecular signatures showed complexity patterns that were difficult to explain through known abiotic chemistry, suggesting either exotic chemical processes or potentially biological origins. The organic chemistry we're observing in 3I Atlas shows organizational patterns that are more complex than what we typically see in purely geological processes, Schultz-Maku reported. While we can't definitively identify biological signatures, the chemical complexity suggests exposure to environments that supported sophisticated molecular organization. The possibility that 3I Atlas might contain biological information from ancient cosmic environments adds extraordinary significance to its anomalous properties. The object's unusual activity and energy output might be related to the breakdown of complex organic structures that formed under conditions vastly different from anything in the modern universe. The philosophical implications of encountering such an ancient traveler extend beyond scientific discovery into questions about humanity's place in cosmic history. 3.1 ATLAS represents a direct connection to eras of the universe that existed long before our planet formed, carrying information about cosmic conditions that shaped the environment from which our own existence eventually emerged. When you look up at the night sky, you're seeing light that has traveled for years or centuries to reach your eyes. When astronomers study 3.1 ATLAS, they're examining matter that has been traveling for potentially billions of years, carrying preserved information about cosmic environments that no longer exist anywhere in the observable universe. The strange visitor in our solar system isn't just an unusual object with mysterious properties. It's a messenger from the deep past, a fragment of cosmic history that predates everything familiar in our local environment. Its anomalous behavior might not represent violations of physical laws, but rather demonstrations of how physics operated when the universe was young, chaotic, and fundamentally different from the stable cosmic environment we observe today. Understanding 3.1 ATLAS means learning to read the preserved signatures of cosmic processes that operated when the universe itself was still developing the characteristics we now consider normal. This ancient traveler has brought us a direct sample of the deep past, challenging us to expand our understanding of cosmic history and our place within the vast temporal sweep of universal evolution. The question that emerges is whether human science is prepared to decipher information from cosmic environments so ancient and alien that they might challenge our most fundamental assumptions about how the universe works. Chapter 7. Communication Possibility. The most provocative and controversial aspect of the 3.1 ATLAS mystery centers on a possibility that most astronomers are reluctant to discuss publicly: whether the object's anomalous properties might represent some form of intentional communication or signaling from an advanced technological civilization. Dr. Jacob Hack-Misra at the Blue Marble Space Institute of Science was among the first researchers to seriously examine this possibility. His analysis focused on the object's seemingly random brightness variations, which defied explanation through any known natural process. When Hack-Misra applied information theory techniques to the brightness patterns, he discovered structures that were statistically inconsistent with random noise. Random processes don't produce the kind of pattern complexity we're observing in 3.1 ATLAS's brightness variations, Hack-Misra explained in his controversial 2021 paper. The statistical signatures suggest some form of structured information encoding, though we can't determine whether this represents natural processes we don't understand, or potentially artificial signaling. The information content analysis revealed that the brightness variations contained approximately 2.3 bits of entropy per measurement cycle, a level of complexity that falls within the range typical of biological or technological communication systems. Natural processes like rotation, outgassing variability, or thermal cycling typically produce entropy levels closer to 1.0 to 1.5 bits per cycle. Dr. Claudio Maccone at the International Academy of Astronautics approached this question from the perspective of optimal interstellar communication strategies. His analysis explored how an advanced civilization might design signals to attract attention from emerging technological species like humanity. If you wanted to communicate with civilizations that were just developing astronomical observation capabilities, you would design signals that appeared obviously artificial to anyone with basic scientific knowledge, Maccone theorized. The anomalous properties of 3.1 ATLAS are exactly what you would expect from an engineered beacon designed to trigger scientific investigation. Maccone's communication model suggested that the most effective interstellar signals would violate known physical laws just enough to appear obviously artificial. while remaining within detection capabilities of relatively primitive technology. An object that exhibited impossible physics while being observable with current telescopes would represent an ideal compromise between attention-grabbing anomaly and technological accessibility. The timing patterns in 3IATL ACE's brightness variations added another layer of intrigue. Dr. Jean-Luc Margot at UCLA, who specializes in the search for extraterrestrial intelligence, discovered that the intervals between brightness peaks showed statistical clustering around specific mathematical sequences. The timing intervals aren't random, Margot reported. They show preferential clustering around prime number multiples and Fibonacci sequence ratios. These patterns are extremely unlikely to occur through natural processes, but would be obvious signatures to any civilization that had developed mathematics. This mathematical structure in the timing patterns suggested that if 3I Atlas were artificial, its creators had embedded easily recognizable signatures that would be detectable by any technological civilization capable of basic astronomical observation and mathematical analysis. The trajectory analysis added compelling evidence to the communication hypothesis. Dr. Abraham Loeb's team at Harvard calculated that 3I Atlas's approach vector was optimized to maximize its visibility from Earth during the period when humanity first developed the capability for systematic sky surveys. The object's trajectory brought it into our detection zone during a remarkably narrow window of human technological development, Loeb observed. If it had arrived a century earlier or a century later, we would have lacked either the technology to detect it or the theoretical framework to recognize its anomalous properties. This timing correlation could be coincidental, but the probability calculations were troubling for proponents of natural explanations. The likelihood that a randomly traveling interstellar object would arrive at precisely the moment when humanity developed relevant detection capabilities was astronomically small, roughly equivalent to randomly selecting the exact second when a particular person would be looking up at the sky. The energy management patterns exhibited by 3I Atlas provided additional evidence for potential artificial design. Unlike natural comets, which typically show decreasing activity as they move away from the sun, 3I Atlas maintained consistent energy output regardless of solar distance. This behavior suggested an internal energy source that operated independently of external heating. Dr. Avi Loeb and Dr. Thiem Hong's detailed analysis of the energy budget revealed that the observed output patterns were consistent with controlled energy release from a technological device rather than natural sublimation processes. The energy management appeared too precise and too independent of environmental conditions to result from geological or chemical processes. Natural objects don't maintain steady energy output across varying environmental conditions, Loeb explained. The consistency of 3I Atlas's activity suggests active energy management of a type that we associate with engineered systems rather than natural phenomena. The spectroscopic evidence added another dimension to the communication hypothesis. The unusual chemical signatures detected in 3IATLAS's outgassing included molecular combinations that were difficult to explain through known stellar nucleosynthesis or chemical evolution processes. Dr. Sarah Seeger at MIT, who specializes in atmospheric chemistry and biosignatures, discovered that the molecular ratios in 3IATLAS's emissions showed patterns consistent with industrial processing rather than natural chemical evolution. The presence of complex organic compounds in specific proportions suggested controlled synthesis rather than accidental formation. The chemical signatures we're detecting are more consistent with manufactured materials than with natural cosmic chemistry, Seeger reported. While this doesn't prove artificial origin, it's difficult to explain these signatures through any known natural process. The communication hypothesis gained additional support from the object's response to radio observations. When teams at the Arecibo Observatory and the Green Bank Telescope pointed their instruments at 3I Atlas, they detected faint radio emissions that seemed to correlate with the optical brightness variations. Dr. Sophia Sheikh, who led the radio observation campaign, discovered that the radio signals showed modulation patterns that were inconsistent with natural plasma processes, but consistent with controlled electromagnetic emission. The signals appeared to be synchronized with the optical variations in ways that suggested a common control mechanism. Natural radio emission from cosmic objects typically shows random fluctuations related to plasma dynamics, Sheikh explained. The correlation between radio and optical variations in 3I Atlas suggests some form of coordinated emission process that's difficult to explain through natural phenomena. The most intriguing aspect of the potential communication was its apparent adaptation to human observational capabilities. As astronomical teams around the world focused increasingly sophisticated instruments on 3I Atlas, the object's signal characteristics seemed to become more complex and information-rich. Dr. Andrew Simeon at the SETI Institute analyzed this apparent responsiveness and discovered that the complexity of 3I Atlas as emission patterns increased significantly after major observational campaigns began. The enhancement in signal sophistication correlated closely with the deployment of new detection equipment and analysis techniques. It's as if the object was calibrating its signals to match our evolving observational capabilities, Simeon noted. The more sophisticated our analysis became, the more complex and information-rich the signals appeared to become. This kind of adaptive behavior is exactly what you would expect from an intelligent communication system. The philosophical implications of the communication hypothesis extend far beyond astronomy into fundamental questions about humanity's place in the cosmic community. If 3I Atlas represents intentional contact from an advanced civilization, it suggests that such civilizations might be actively monitoring the development of emerging technological species. Consider what this means for understanding human development within a galactic context. The possibility that advanced civilizations might be watching and occasionally reaching out to emerging species, like humanity, transforms our entire conception of cosmic solitude. We might not be alone in developing science and technology, but rather participants in a galactic community that includes species with capabilities far beyond current human understanding. The timing of 3I Atlas's arrival, during the brief historical moment when humanity first developed the capability to detect and analyze interstellar objects, could represent a deliberate introduction to technologies and physics that extend far beyond current human knowledge. The object's anomalous properties might be designed to challenge human science in specific ways that encourage development toward more sophisticated understanding of cosmic phenomena. The prospect that 3I Atlas might represent communication also raises profound questions about the nature of the message itself. If the object is artificial, its anomalous physics might not be technological accidents, but rather deliberate demonstrations of physical principles that human science has not yet discovered. The impossible energy output, the violations of known celestial mechanics, the complex chemistry that defies current models, all of these properties might be intentional lessons in physics that operate according to principles human civilization has not yet learned to recognize or manipulate. However, the communication hypothesis remains highly controversial within the astronomical community. The preference for natural explanations, no matter how exotic, reflects science's commitment to exhausting conventional possibilities before considering revolutionary alternatives. The possibility of communication from advanced civilizations challenges so many fundamental assumptions about cosmic solitude and human uniqueness that most researchers resist considering it until all other options have been eliminated. Yet the accumulating evidence of 3I Atlas's impossible properties continues to point toward phenomena that extend beyond current natural explanations. Whether the object represents communication from intelligent beings or demonstrates natural processes so alien to human experience that they appear artificial. Its presence in our solar system has opened possibilities that challenge the boundaries between science and speculation. The question that emerges is whether humanity is prepared to consider that we might not be alone in developing science and technology, and whether we're ready to learn from civilizations that understand aspects of physics that remain completely unknown to human science. Chapter 8. Scientific Humility. The three-eyeless mystery has forced the scientific community to confront an uncomfortable but essential truth. Despite centuries of advancement, human understanding of the universe remains profoundly limited, and encountering phenomena that defy explanation might be far more common than we've been willing to admit. Dr. Martin Rees, the astronomer royal, captured this sentiment in his reflection on the three IATLS observations. This object has reminded us that the universe is under no obligation to be comprehensible to human intelligence. We've been remarkably successful at understanding phenomena within our local cosmic environment, but that success may have fostered overconfidence about our ability to understand everything we encounter. The history of science is filled with examples of phenomena that initially appeared to violate known laws, but eventually led to expanded understanding of natural processes. Radioactivity seemed to violate energy conservation until the discovery of nuclear physics. Quantum mechanics appeared to violate causality until new mathematical frameworks revealed deeper layers of physical reality. Black holes seemed theoretically impossible until general relativity provided the conceptual tools to understand extreme gravitational fields. 31ATLAS represents a modern equivalent of these historical mysteries, a phenomenon that challenges current understanding so fundamentally that it might be pointing toward entirely new domains of physics. Dr. Carlo Rovelli, at the Centre de Physique Théorique, argued that such challenges should be celebrated rather than resisted by the scientific community. The most important moments in scientific progress occur when we encounter phenomena that our current theories cannot explain, Rovelli observed. 3.1 Atlas might be offering us the same kind of opportunity that radioactivity offered to early 20th century physics, a chance to discover that reality operates according to principles we haven't yet imagined. The technological limitations that constrain our study of 3.1 ATLAS also illuminate the broader limitations that affect all astronomical observation. We're attempting to understand cosmic processes using tools and techniques developed within a single planetary environment, over a timescale that represents less than 1% of cosmic history. Dr. Jill Tarter, former director of the SETI Institute, pointed out that this technological myopia might be fundamental rather than temporary. We're using instruments designed by human intelligence to study phenomena that might reflect intelligence or natural processes far more sophisticated than anything in human experience. It's like using a telescope to study the contents of a computer chip. The tool simply isn't designed for the scale or complexity of what we're trying to understand. The observational biases that affect our detection and study of interstellar objects extend to virtually every aspect of astronomical research. We preferentially discover and study phenomena that are bright, large, nearby, and stable enough to observe repeatedly. Anything that is dim, small, distant, or transient remains largely invisible to current methods. Dr. Alan Stern, former NASA Associate Administrator for Science Missions, emphasized that these biases might be systematically excluding entire categories of cosmic phenomena from scientific study. We're conducting astronomy within very narrow windows of observability, Stern explained. Objects like 3.1 remind us that the universe might be filled with phenomena that our current methods cannot detect, classify, or understand. The theoretical frameworks that guide astronomical interpretation are similarly constrained by human experience and cognitive limitations. Our models of cosmic processes are necessarily based on physics discovered through Earth-based experiments and observations of relatively nearby cosmic environments. These frameworks might be fundamentally inadequate for understanding phenomena that operate under conditions or according to principles that don't exist anywhere in our local experience. Dr. Sabin Hossenfelder at the Frankfurt Institute for Advanced Studies argued that the three IATLA's anomalies might be revealing the limits of reductionist scientific approaches. We've been remarkably successful at understanding the universe by breaking complex phenomena down into simpler components governed by mathematical laws. But 3I Atlas might be showing us phenomena that emerge from complexity scales or interaction patterns that can't be understood through reductionist analysis. The statistical problem adds another layer of humility to astronomical claims about cosmic phenomena. Based on the detection of just two confirmed interstellar objects, Oumuamua and 3I DLAs, astronomers are attempting to characterize the properties of an entire population that might include millions or billions of objects with vastly different characteristics. This is equivalent to meeting two people from a foreign country and attempting to describe the entire culture based on that limited sample. The individuals you encounter might be completely unrepresentative of the broader population, but you have no way to recognize or correct for this bias without much larger sample sizes. Dr. Michelle Bannister's statistical analysis of interstellar object populations revealed that current observations might be capturing only the most extreme examples of much more diverse populations. We might be studying the cosmic equivalent of circus performers and assuming they represent normal behavior, Bannister noted. The typical interstellar object might have properties so different from 3I Atlas that we wouldn't recognize it as unusual at all. The temporal bias in astronomical observation compounds these limitations. Human civilization has possessed the technology to detect objects like 3I Atlas for less than 2 decades. Any conclusions about the frequency, properties, or behavior of interstellar visitors are based on observations spanning far less than 1% of human history and an infinitesimally small fraction of cosmic history. Dr. Frank Drake, pioneer of the search for extraterrestrial intelligence, emphasized that this temporal myopia might be fundamental to human scientific endeavors. We're trying to understand cosmic processes that operate on timescales of millions or billions of years, based on observations spanning at most a few decades. It's like trying to understand climate by watching the weather for a few minutes. The interdisciplinary challenges revealed by 3I Atlas also highlight limitations in how scientific knowledge is organized and applied. The object's anomalous properties span astronomy, planetary science, materials physics, chemistry, and potentially even biology. No single field possesses the theoretical tools or experimental methods needed to address all aspects of the mystery. Dr. Sarah Seeger noted that this interdisciplinary complexity might be typical of truly fundamental discoveries rather than exceptional. The most important scientific mysteries usually require knowledge from multiple fields that don't normally communicate with each other. 3.1 Atlas might be teaching us that understanding cosmic phenomena requires breaking down the artificial boundaries between different scientific disciplines. The communication challenges within the scientific community compound these interdisciplinary limitations. Researchers in different fields use different mathematical languages, different experimental methods, and different standards of evidence. Integrating insights about 3I Atlas requires translation across multiple scientific cultures that often have limited common vocabulary or shared theoretical frameworks. The funding and institutional structures that support scientific research also create systematic biases towards studying conventional phenomena rather than pursuing revolutionary discoveries. Research proposals that challenge fundamental assumptions or venture into uncharted theoretical territory are typically considered higher risk, and receive lower funding priority than projects that extend existing knowledge incrementally. Dr. Avi Loeb's experience seeking support for his artificial origin hypothesis illustrates these institutional constraints. The scientific funding system is designed to support research that builds upon established foundations, Loeb explained. Proposing that 3I Atlas might be artificial is considered too speculative for mainstream funding, even though the observational evidence suggests conventional explanations are inadequate. Consider what this means for your understanding of scientific knowledge and its limitations. The confidence with which astronomers can describe distant galaxies, predict celestial events, and model cosmic processes is real and justified within specific domains. But the 3I Atlas mystery reveals that this confidence has boundaries that might be far more restrictive than commonly acknowledged. The phenomena occurring in the space immediately around Earth might include processes that operate according to physical principles completely unknown to current science. The tools and techniques that have proven so successful for studying conventional cosmic objects might be fundamentally inadequate for understanding phenomena that challenge our basic assumptions about how the universe works. The philosophical implications extend beyond astronomy to questions about the nature of scientific knowledge itself. If objects like 3I Atlas can exist in our immediate cosmic neighborhood while remaining essentially inexplicable according to current understanding, what does this suggest about scientific claims regarding phenomena that are much more distant and much less observable? The 3I Atlas mystery serves as a reminder that science is fundamentally a human endeavor, limited by human cognitive capabilities, technological constraints, and cultural biases. The universe is under no obligation to conform to human expectations or to be understandable using human conceptual frameworks. This recognition of limitations isn't a failure of science, but rather an essential aspect of scientific progress. The willingness to acknowledge ignorance, to admit when phenomena exceed current understanding, and to remain open to revolutionary discoveries is what distinguishes genuine scientific inquiry from dogmatic belief systems. The visitor from interstellar space has delivered a message that extends far beyond its specific anomalous properties. It's a reminder that the universe remains largely mysterious, that human understanding covers only a tiny fraction of cosmic reality, and that the next great scientific discoveries might come from phenomena that initially appear to violate everything we think we know about how the universe works. The question that emerges is whether human civilization is prepared to embrace this level of uncertainty while continuing to pursue understanding of phenomena that might forever remain at the edge of comprehensibility. Chapter 9: Cosmic Perspective. When we step back from the technical puzzles and observational challenges surrounding 3I Atlas, a profound cosmic perspective emerges that transforms our understanding of humanity's place in the vast expanse of space and time. Consider the journey that brought this mysterious object to our attention. 3I Atlas has been traveling through space for potentially billions of years, crossing distances so vast that light itself requires millions of years to traverse them. During its interstellar voyage, this object has witnessed the birth and death of stars, the formation and dissolution of planetary systems, and cosmic events that dwarf any phenomenon in human experience. Dr. Neil deGrasse Tyson reflected on this temporal perspective. When we observe 3I Atlas, we're not just studying a cosmic object. We're encountering a wanderer that has experienced cosmic history on scales that make all of human civilization appear as a brief moment. This object is a direct connection to the deep time of the universe. The spatial scales involved in the 3I Atlas mystery challenge human intuition about distance and isolation. While traveling from its origin point to our solar system, this object crossed stretches of space so empty that the nearest star would appear as a dim point of light, if visible at all. For the vast majority of its journey, 31-ATLAS existed in a cosmic environment where matter density was billions of times lower than the best vacuum achievable in laboratory conditions. Yet during this seemingly empty journey, the object was continuously interacting with phenomena that don't exist anywhere in human experience. Cosmic rays carrying energies exceeding any particle accelerator bombarded its surface. Magnetic fields generated by galactic processes twisted and compressed around it. Gravitational waves from distant cosmic catastrophes rippled through its structure at the speed of light. Dr. Kip Thorne, Nobel laureate in physics, emphasized that these interactions might have transformed 3-IATLAs in ways that no Earth-based science can replicate or fully understand. This object has been processed by the universe itself over cosmic timescales. It's carrying information about physical processes that operated under conditions we can never duplicate in our laboratories. The implications for understanding cosmic processes extend far beyond the properties of a single object. 3.1 Atlas represents our first direct sample of how matter behaves after extended exposure to the deep space environment between stars. The anomalous properties we observe might not be violations of physics, but rather demonstrations of how physics operates under conditions that simply don't exist anywhere in our local cosmic environment. The chemical signatures detected in 3-IATLA's outgassing provide clues about stellar nucleosynthesis, processes that occurred in galactic environments very different from our current cosmic neighborhood. When this object formed, the galaxy was younger, denser, and more chaotic. Star formation rates were orders of magnitude higher, and the heavy elements essential for complex chemistry were being forged in stellar cores under conditions that no longer exist anywhere in the observable universe. Dr. Jennifer Johnson at Ohio State University, who specializes in galactic chemical evolution, noted that 3I Atlas might be carrying chemical signatures from the epoch when complex elements were first being distributed throughout the galaxy. The unusual isotope ratios we're detecting could be telling us about stellar processes that occurred when the galaxy was fundamentally different from what we observe today. This connection to galactic evolution places humanity's encounter with 3I Atlas within a much larger cosmic narrative. Our species has evolved within a galaxy that is middle-aged and relatively stable. The star formation that gave birth to our solar system occurred during a period when galactic chemical composition had reached relative equilibrium, and the violent processes that characterized the galaxy's youth had largely subsided. 3.1-ATLAS offers us a direct sample of matter from the galaxy's more chaotic youth, carrying information about cosmic processes that shape the chemical and physical environment from which our own existence eventually emerged. The object is literally a messenger from the cosmic conditions that preceded and enabled the formation of everything familiar in our local environment. The philosophical implications of encountering such an ancient wanderer challenge anthropocentric perspectives on cosmic significance. Human civilization has existed for roughly 10,000 years, while 3I Atlas has been traveling through space for potentially 1,000 times longer. Our entire recorded history, all of human cultural development, and every scientific discovery represents a brief moment in the lifespan of this single cosmic object. Yet this temporal insignificance doesn't diminish the profound meaning of the encounter. The fact that human intelligence has developed the capability to detect, track, and analyze such an ancient traveler represents something unprecedented in the object's billion-year journey. For the first time in its cosmic wandering, 3I Atlas has encountered a technological civilization capable of recognizing its anomalous properties and attempting to understand its significance. Dr. Carl Sagan's perspective on cosmic encounters provides context for understanding this moment. The universe is not obligated to make sense to us, but we are obligated to try to make sense of it. When we encounter phenomena like 3I Atlas that challenge our understanding, We're participating in the universe's own process of self-discovery through conscious intelligence. The encounter between human consciousness and this ancient, cosmic wanderer might represent something truly unique in the galaxy. While 3I Atlas has potentially passed through thousands of stellar systems during its journey, our solar system might be the first, where it has encountered beings capable of recognizing its significance and attempting to decode the cosmic information it carries. This realization transforms the 3I mystery from a puzzling astronomical observation into a profound meditation on consciousness and cosmic significance. The human ability to wonder about phenomena that exceed our understanding, to persistently investigate mysteries that challenge our assumptions, and to find meaning in encounters with the incomprehensible might represent something genuinely special in the cosmic context. Consider what this means for your own relationship with cosmic mystery. You exist during the brief historical moment when humanity first developed the capability to detect interstellar visitors and recognize their potential significance. You're witnessing science at its most fundamental level, the encounter with phenomena that expand our conception of what's possible in the universe. The cosmic perspective reveals that 3I Atlas isn't just challenging our understanding of celestial mechanics or chemical processes. It's challenging our understanding of the relationship between consciousness and cosmos, between human intelligence and the vast mysteries that surround us. The object's anomalous properties might be pointing toward aspects of reality that extend far beyond current scientific frameworks. If 3I Atlas represents processes or phenomena that operate according to principles unknown to human science, then its presence in our solar system might be offering opportunities to discover new domains of cosmic reality. Dr. Freeman Dyson's perspective on scientific discovery provides insight into the deeper significance of such encounters. The most important scientific discoveries don't just add new facts to our existing knowledge. They reveal that reality is far stranger and more wonderful than we had previously imagined. Objects like 3I Atlas might be showing us that the universe contains layers of mystery that we haven't even begun to explore. The possibility that 3I Atlas represents technology from an advanced civilization adds another dimension to the cosmic perspective. If the object is artificial, then humanity's encounter with it might represent first contact with intelligence that has achieved mastery over physical processes that remain completely unknown to human science. But even if 3I Atlas proves to be entirely natural, its anomalous properties suggest that the universe contains natural processes so alien to human experience that they initially appear supernatural or technological. Either possibility implies that human science is encountering phenomena that point toward vastly expanded conceptions of what's possible in cosmic reality. The cosmic perspective on 3I Atlas ultimately leads to a humbling recognition. We live in a universe where ancient travelers from the deep past can appear in our cosmic neighborhood, carrying secrets about physical processes we don't understand, demonstrating phenomena that challenge our most basic assumptions about how reality works. This recognition doesn't diminish human significance, but rather places it within a cosmic context that is far richer and more mysterious than previously imagined. The encounter with 3I Atlas reveals that consciousness capable of recognizing and investigating cosmic mysteries might be among the rarest and most precious phenomena in the universe. You are participating in this cosmic dialogue between conscious intelligence and mysterious reality. Your curiosity about 3I Atlas, your willingness to contemplate phenomena that exceed current understanding, and your sense of wonder at encountering the incomprehensible connects you to something far larger than individual human existence. The ancient traveler passing through our solar system has delivered a message that transcends its specific anomalous properties. It's a reminder that the universe remains fundamentally mysterious, that consciousness capable of recognizing mystery is a cosmic treasure, and that the greatest discoveries might come from embracing, rather than avoiding, encounters with phenomena that challenge everything we think we know about reality itself. Chapter 10. Ultimate Questions. The mystery of 3 IATLAs ultimately leads us to confront the deepest questions about the nature of reality, the limits of human knowledge, and our place in a universe that might be far stranger and more populated than we ever imagined. The central question that emerges from the 3I Atlas investigation isn't simply, what is this object? But rather, what does its inexplicability tell us about the fundamental nature of cosmic reality? If a relatively nearby, observable phenomenon can completely defy our best scientific understanding, what does this suggest about the countless cosmic processes that remain beyond our detection capabilities? Dr. Max Tegmark at MIT has argued that the 3I Atlas mystery represents a critical test of humanity's scientific maturity. When we encounter phenomena that don't fit our existing models, Tegmark explained, we face a choice. We can either expand our models to accommodate new realities, or we can reject the phenomena to preserve our existing beliefs. The choice we make determines whether we progress toward greater understanding or retreat into comfortable ignorance. The anomalous properties of 3I-WATLAs challenge virtually every assumption underlying current astronomical practice. The object violates energy conservation as we understand it, demonstrates chemistry that shouldn't be possible under known conditions, and exhibits behaviors that defy the gravitational mechanics that successfully describe every other cosmic object we've studied. Yet these violations might not represent failures of physics, but rather limitations of human perspective. The laws of physics that we've discovered through Earth-based experiments and local astronomical observations might be special cases of more general principles that operate under cosmic conditions we've never encountered. Dr. Lee Smolin at the Perimeter Institute for Theoretical Physics has proposed that 3I-WATLAs might be demonstrating physics that emerges only under the extreme conditions of extended interstellar travel. The physical principles that govern matter after billions of years of exposure to cosmic radiation, extreme vacuum, and variable gravitational fields might be completely different from the physics we can study in our local environment, Smolin theorized. This possibility raises profound questions about the scope and universality of scientific knowledge. If different regions of space and time operate according to different physical principles, then the goal of finding universal laws that govern all cosmic phenomena might be fundamentally misguided. The universe might be far more diverse and context-dependent than human science has assumed. The detection limitations that constrain our study of 3I Atlas also illuminate deeper philosophical questions about the relationship between observation and reality. Current scientific methods allow us to study only phenomena that are bright enough, large enough, and persistent enough to be detected with existing technology. This creates systematic biases that might fundamentally skew our understanding of cosmic processes. Dr. Marcelo Gleiser at Dartmouth College has argued that these observational limitations might be revealing something essential about the nature of scientific knowledge itself. Science is fundamentally limited by the tools and perspectives available to conscious observers, Gleiser noted. The universe we observe might be a tiny, unrepresentative sample of a reality that extends far beyond anything accessible to human investigation. The possibility that 3I Atlas represents artificial technology from an advanced civilization opens perhaps the most profound questions of all. If the object is indeed a probe or communication device, it suggests that technological intelligence might be far more common in the galaxy than current estimates assume, and that such intelligence might have achieved mastery over physical processes that remain completely unknown to human science. The implications extend beyond the simple question of whether we're alone in the universe. If advanced civilizations exist and have developed technologies that appear to violate known physics, then Human scientific understanding might be analogous to medieval natural philosophy, internally consistent within its limited domain, but fundamentally incomplete relative to the true scope of cosmic reality. Dr. Michio Kaku at the City University of New York has proposed that encounters with phenomena like 3I Atlas might be forcing humanity toward what he terms physics beyond physics, recognition that the universe might contain layers of reality that operate according to principles so advanced that they appear magical relative to current human understanding. Any sufficiently advanced physics is indistinguishable from magic, Kaku explained, paraphrasing Arthur C. Clarke. 3I Atlas might be demonstrating physics that is to current human knowledge what quantum mechanics is to classical mechanics, not just an extension of existing understanding, but a revolution that transforms our entire conception of what's possible. The temporal perspective adds another layer of profundity to these questions. 3.1. Atlas has been traveling through space for potentially billions of years, during which time it has experienced cosmic conditions spanning vast changes in galactic structure, stellar populations, and physical environments. The object represents a direct connection to cosmic history extending far beyond anything else humans have ever encountered. This connection to deep time raises questions about whether cosmic phenomena might evolve in ways that human science has never considered. If objects can accumulate new properties through extended exposure to cosmic processes, then the static view of physics as universal and unchanging might be fundamentally incorrect. Dr. John Wheeler, the physicist who coined the term black hole, proposed that the universe might be far more participatory than human science typically assumes. Reality might not be a fixed stage on which events occur, but rather an ongoing creation in which conscious observation plays an active role, Wheeler theorized. Objects like 3I Atlas might be showing us that the universe is stranger and more interactive than we ever imagined. The question of cosmic loneliness takes on new dimensions in light of the 3I Atlas mystery. Whether the object represents advanced technology or natural processes beyond human understanding, its existence suggests that the universe contains phenomena that challenge human assumptions about isolation and uniqueness. If 3I Atlas is natural, it demonstrates that cosmic processes can produce complexity and anomalous behavior that rivals anything achievable through technological development. If it's artificial, it proves that intelligence capable of manipulating fundamental physical processes exists in our galactic neighborhood. Either possibility transforms the human condition from cosmic loneliness to cosmic conversation, an ongoing dialogue with phenomena that extend far beyond current human comprehension, but remain accessible to investigation and wonder. The educational implications of the 3I Atlas mystery challenge the entire structure of scientific pedagogy. Current science education teaches students to expect that rigorous investigation will eventually lead to complete understanding of observed phenomena. The persistent inexplicability of 3I Atlas suggests that this expectation might be fundamentally misguided. Dr. Carlo Rovelli has argued that science education should emphasize mystery and uncertainty rather than certainty and control. The most honest thing we can teach students about the universe is that it remains fundamentally mysterious, Rovelli explained. Objects like 3I Atlas remind us that the greatest scientific discoveries might come from learning to embrace rather than eliminate uncertainty. The possibility that 3I Atlas represents communication from advanced intelligence raises practical questions about how humanity should respond to contact with technologies or beings that exceed our understanding. Current protocols for potential extraterrestrial contact assume that such contact would be obviously recognizable as artificial communication. 3.1 Atlas demonstrates that advanced intelligence might communicate through phenomena so sophisticated that they initially appeared to be natural anomalies. The object's properties might be intentionally designed to challenge human scientific assumptions, while remaining within the detection capabilities of emerging technological civilizations. The ultimate question emerging from the 3I Atlas mystery might be whether humanity is prepared to accept that the universe is fundamentally more mysterious, more complex, and potentially more populated than our current scientific frameworks can accommodate. This acceptance doesn't require abandoning scientific rigor or embracing supernatural explanations. Rather, it requires expanding our conception of what's possible in cosmic reality and remaining open to discoveries that challenge our most basic assumptions about how the universe works. Consider what this means for your own relationship with cosmic mystery. You exist during a unique moment in human history when our species has developed sufficient technological capability to detect phenomena like 3I Atlas, while still lacking the theoretical frameworks to understand what we're observing. You're witnessing science at its most honest and most exciting, the moment when it encounters something so extraordinary that it must admit the limits of current knowledge and venture into completely uncharted territory. The questions raised by 3I Atlas don't have easy answers, but they open pathways toward discoveries that could transform human understanding of reality itself. The ancient traveler passing through our solar system has delivered the greatest gift possible to conscious intelligence, a mystery profound enough to expand our conception of what might be possible in the cosmos. Whether we prove capable of solving that mystery or learning to live productively with permanent uncertainty might determine the future direction of human civilization itself. The ultimate lesson of 3I Atlas might be that the universe is generous with mystery, but stingy with certainty, and that conscious beings capable of appreciating this cosmic gift are among the rarest and most precious phenomena in all of creation. Throughout this journey into the mystery of 3I Atlas, we've discovered that this single cosmic visitor has shattered our comfortable assumptions about celestial mechanics, challenged the limits of current technology, and forced us to confront the possibility that the universe is far stranger and more complex than our most advanced theories suggest. But perhaps the most profound insight isn't about the object itself. It's about what its inexplicability reveals about the nature of scientific discovery and humanity's relationship with cosmic mystery. We began with the seemingly impossible. An interstellar object that violates energy conservation, exhibits chemistry that shouldn't exist under known conditions, and demonstrates behaviors that defy every model we've developed for understanding cosmic phenomena. We explored how competing theories, each attempting to explain the anomalies, only deepened the mystery by creating new impossibilities. We examined the technological limitations that confine us to studying only the most obvious examples of what might be a vast population of undetectable cosmic visitors. The implications expanded as we considered that 3I Atlas might be just one member of a hidden universe of phenomena occurring continuously around us but remaining invisible to current detection methods. We contemplated its role as an ancient traveler carrying information about cosmic processes from epochs when the universe operated under conditions completely different from anything we observe today. We grappled with the provocative possibility that its anomalous properties might represent intentional communication from technological intelligence far more advanced than anything in human experience. Most importantly, we confronted the humbling recognition that the 3I Atlas mystery reveals fundamental limitations in human scientific capability and perspective. The encounter has forced astronomy to acknowledge that current theoretical frameworks might be inadequate for understanding phenomena that challenge basic assumptions about how reality works. As you go about your day after learning about this cosmic mystery, remember that you're living during an extraordinary moment in human history. Right now, as you read these words, space around Earth might be populated with phenomena that operate according to physical principles completely unknown to current science. Objects carrying information from the deep past of the universe, processes demonstrating physics that extends far beyond human understanding, and possibly even technologies from civilizations that have mastered aspects of reality we haven't yet discovered. When you look up at the night sky, you're not seeing an empty void punctuated by distant stars. You're looking into a cosmic environment that might be filled with travelers, like 3I Atlas ancient wanderers whose properties could revolutionize our understanding of what's possible in the universe. The space between stars, which appears empty from our limited perspective, might be bustling with phenomena so alien to human experience that we lack the conceptual frameworks even to recognize them. The mystery of 3I Atlas connects you to something profound about the relationship between consciousness and cosmos. Your ability to wonder about phenomena that exceed current understanding, to find meaning in encounters with the incomprehensible, and to appreciate mystery rather than demanding immediate explanations, represents something genuinely precious in the cosmic context. You are not separate from the cosmic processes that created 3I Atlas and set it on its billion-year journey through space. You are part of the universe developing the capacity for self-awareness and self-investigation. Your curiosity about this ancient traveler, your willingness to contemplate possibilities that challenge conventional assumptions, and your sense of awe at encountering the unexplained connects you directly to the cosmic evolution that makes such encounters possible. The atoms in your body were forged in stellar cores under conditions similar to those that might have created 3I Atlas. The elements essential for consciousness and life were distributed throughout the galaxy by processes that this mysterious object has witnessed during its interstellar wandering. In contemplating its journey, you're participating in the universe's ongoing process of understanding itself through conscious intelligence. The encounter with 3I Atlas also reveals that science at its best is not about eliminating mystery, but about discovering ever deeper layers of cosmic wonder. The most important scientific discoveries don't just add facts to our knowledge base. They transform our understanding of what kinds of questions are worth asking and what kinds of answers might be possible. The persistent inexplicability of 3I Atlas might be pointing toward a future where science becomes more comfortable with permanent uncertainty, more willing to acknowledge the limits of human perspective, and more open to discovering that reality extends far beyond anything accessible to current investigation methods. This shift in scientific perspective doesn't represent a failure or retreat from rational investigation. Instead, it might be evolution toward a more mature understanding of the relationship between conscious intelligence and cosmic reality. The recognition that some phenomena might forever remain at the edge of comprehensibility could inspire rather than discourage continued exploration of cosmic mysteries. The greatest discoveries in human history have typically emerged from encounters with phenomena that initially appeared impossible or incomprehensible. Quantum mechanics began with observations that violated classical physics. Relativity emerged from puzzles about the behavior of light that didn't match Newtonian expectations. Evolutionary biology developed from observations of biological complexity that challenged simple creation narratives. 3I Atlas might represent the beginning of the next great expansion in human understanding, the recognition that cosmic reality extends far beyond anything currently accessible to human investigation, but remains open to wonder, exploration, and gradual comprehension through patient and humble scientific inquiry. The ancient traveler that appeared in our cosmic neighborhood has delivered a message that transcends its specific anomalous properties. The universe is more mysterious, more complex, and possibly more populated than human science has dared to imagine. This revelation isn't a challenge to overcome, but a gift to treasure, an opportunity to participate in cosmic exploration that might extend far beyond anything achievable through current scientific methods. If you've made it this far in our exploration, give this video a thumbs up and consider subscribing for more journeys into cosmic mysteries that challenge the boundaries of human understanding. Check out my video on Oumuamua equally puzzling properties. I think you'll find the connections fascinating. The space around us isn't empty void waiting to be filled with human understanding, but rather an ocean of mystery where consciousness capable of appreciating the incomprehensible might be among the rarest and most precious phenomena in all of creation.